Assalamu alaikum. In the previous video, we have discussed few parameters related with circular motion. In this video, we will discuss tangential acceleration, which is another parameter related with circular motion. For that, I consider a circular path along which an object, let us say, so as an object which moves along the circumference of this circle, which has got a center represented by letter O. Initially, this object is found to be present at a point A. Now, after time delta t, what is this delta? Now, this symbol is named as delta. It is used to represent a small change. Okay, currently speaking, it is used to represent the change. It represents a change. So, whenever we use a variable, we just keep changing its value with time. We use this symbol delta. So, a delta t actually represents the change in time. Clear? In time delta t, the object changes its position. It moves along the circle, along the circumference of this circle, and reaches to a new position. See, after time delta t, it has changed its position. It has gone to a new position. You see, it is B. Now I connect the object to the center of this circle. The same I do here as well. Now when it moves, along with it, this line which connects the center to the object also move. So it sweeps an angle. This angle swept by the object or by this radius, this line represents angular displacement. Say, for my convenience, I take this angle to be equal to delta t. So delta t is the angular displacement for time delta t. Clear? Delta t, angular displacement. And then here, this line which connects the object to the center actually provides us the radius of this circular path. Am I right? Now I'll go ahead. I'm going to relate these three things: delta t, delta theta, r, and the arc length. Here, the arc length, the distance between A and B along the circumference is taken as delta S. Clear? Now we know angle theta, which represents angular displacement, is related with arc length, length of the arc divided by radius of the arc gives us the angular displacement. This we have learned earlier. Similarly, here we have the angular displacement. In our case, the angular displacement is delta theta, which is equal to length of the arc is nothing but delta S. And what is the radius here? R. So see, in this three, if you look at these three quantities, you will find except the radius, other two parameters are provided with the delta. This to show that they change with the time. But here radius of this circle remains same throughout the motion of the object, because the object is in uniform circular motion. Now in uniform circular motion, the magnitude of speed remains the same. No, it do not change. You know that. Yeah. So it is written as a R, not a delta R. Okay. The next, I'll make a small change to this. Now, before doing so, I take this equation as equation number 1. Now, I'll divide this equation. Equation number 1 is divided with the delta t. If I do so, what I'll get? I'll get this delta theta divided by delta t. Now, when I make any changes to this side, the same thing I have to do on the other side as well. See, let's say this one, yes, yeah, delta s divided by delta t. Now here this one kept as such 1 upon r. Okay, actually what I have done, instead of writing as delta s upon r, this can be written as delta s multiplied with the 1 upon r. Okay, this is how we obtain 1 upon r here in this equation. Clear? Next, here rate of change of angular displacement is nothing but angular velocity. Now before doing that, suppose the limit of delta t tends to 0. Limit of delta t tends to 0. Then delta t upon delta theta upon delta t can be written as d theta upon dt. In the similar way, this will become ds upon dt. Clear? So, similar way, when the limit delta t tends to 0, delta s upon delta t will turn into ds upon dt. What does it mean? When I say limit delta t tends to 0, it means when a change in time is 2 or nearing 0, that means the change in time is very near to 0. For a small change, this can be written as the delta can be replaced with a d. Here d represents a small change. Clear? So this equation is written in differential form as d theta upon dt equals to ds upon dt multiplied with 1 upon r. Clear? We know very well, we know that d theta, rate of change of angular displacement, change in angular displacement with time, provides us angular velocity. Okay, in a similar way, the rate of change of displacement, change in displacement with time, gives us velocity, linear velocity. Clear? This angular velocity, this linear velocity. So by keeping these things in mind, using these things here, I get a new form of the equation. The place of d theta upon dt, I write omega, which is equal to ds upon dt is v, and here I have 1 upon r. Now I take r to the another side. Here it divides with v. When it is taken to the another side, it will multiply. So what I'll get this omega r equals to v. Okay, this is the relationship between linear velocity and angular velocity. But here, velocity is a vector quantity and the angular velocity is also a vector quantity. So they have to be written in vector form, this way, in vector form. No, actually we have to relate them in this manner. V equals to V vector equals to omega vector cross r vector. Now this provides us the cross product, vector product. Okay, this is the correct method of writing the relation between linear velocity and angular velocity, because they possess direction along with the magnitude. So I take this as equation number 2, this is as equation number 3. But for circular motion, equation number 2 is valid. Okay. In circular motion, okay, in circular motion, here angular velocity omega and r, that is the radius of the circle, acts perpendicular to each other. Acts perpendicular. No, perpendicular means making an angle of 90 degrees with each other, perpendicular to each other. So how do they act perpendicular to each other? Let me show this to you with the help of a diagram. Suppose this is a circular path. No, I have shown the circle in this plane. Clear? This is the circle, for example. When I show this circle in another plane, it appears something like this. It is not ellipse, it is circle in another plane. Okay. Here, this is the center of this circle. This is the radius of this circle. If the object move in anti-clockwise direction, in this direction, then this line, which is nothing but axis of rotation, provides us angular velocity. Here angular velocity acts along this line, along axis of rotation. Clear? See? Here angular velocity is acting perpendicular to the radius of the circular path. Got it? So this we get this statement. Fine. Now I expand the equation number 3 on expanding equation number 3. What I get if I expand this? Well, it's a vector product. Now look at here carefully. When we expand a vector product, we get this, the omega r sine theta. Okay, and here the angle is 90 degrees. So the place of theta, I write this. What do I write? I write 90 degree. So V vector is equal to omega r sine 90. What is sine of 90? Sine of 90 is equal to 1. So in the place of sine of 90, I write 1. So what I get? Obviously I get this. V equals to r omega. V vector is equal to r omega. Clear? But you have to bother about all these things. Actually, we deal with an object which is in a circular motion. So equation number 2 is valid for us. Whether it has got whether the parameters present here have got the direction or not. We don't bother about that. Because in a circular motion, the direction of the object changes continuously, but the magnitude remains the same. Okay, so from equation 2, what is this equation number 2? Yes, V is equal to r omega. Now I'm going to differentiate this. Differentiating equation number 2 with respect to time. Equation number 2 with respect to time. What do I get if I do so? I differentiate this equation. When differentiating, we will get this. First, dv upon dt. First order differential of velocity with respect to time. Clear? Then here r is a constant. See, it remains same throughout. In uniform circular motion, the magnitude of the velocity vector remains the same. So the object keeps moving in a particular path without changing its track. Clear? Fine. This we have learned earlier. Now here, so r is a constant. Here r is a constant. R is a constant. That is obvious from the diagram. So it is kept as such. We do not differentiate a constant. Then omega is differentiated with respect to time as d omega upon dt. Now, when we differentiate velocity with time, we get the acceleration, linear acceleration. What is that? dv upon dt is linear acceleration from letter A. In the similar way, d omega upon dt is nothing but angular acceleration. This we have learned the previous video. Okay. And so dv upon dt is A equals to r as such. D omega upon dt is alpha. No, this is the relation. And here dv upon dt is actually a tangential acceleration. So I write it as a t. This is how we get a tangential acceleration, and this tangential acceleration acts along the velocity. Okay. On the velocity vector. Let me show this to you in the diagram. So this is the diagram. The same I will use to show the direction of. Let me draw here the diagram separately. This is the circular path, and this is the center of the circle. Okay. And the next, the object is present here at point A. Now, when time is 0, then after some time it reaches to a new position, that is B. Now, I connect A to the center, and the same thing I do with the B as well. Okay, this is the radius. of the circle. Now, when the object is present at point A and it moves in this direction, then this tangent provides us the velocity vector. Okay, the direction of the velocity vector, which is perpendicular to the radius. The similar way, when the object reaches the point B, to a new position, there, if I draw a tangent, what is tangent? Tangent is a line which goes touching the curve or the circle. Okay, see, this line goes touching the circle. It doesn't intersect it, but goes touching it. This provides the direction of the velocity vector. Okay, now again it is perpendicular to the radius. It is obvious from the diagram. Now you can see here the velocity vector is acting in this particular direction, where at point B it has changed its direction. So only the direction changes, but the magnitude remains same. That is why it is the orbit is keep rotating in the same track throughout its motion. Clear? Otherwise, it would have, if the velocity increases, then it will move away from the center. If it gets slower, then it will start coming towards the center. And at what point, when the orbit stops moving, it will reach the center. But that doesn't happen here. The velocity is remaining same throughout the motion. So the object moves in this particular circular path. Fine. So here this is the direction of a velocity. Along this direction, the tangential acceleration is found to be acting. Clear? The direction, along this arrow line. So that's all about the tangential acceleration. I hope the video is useful. If you have any kind of doubt relevant to the topic, can you put a question in the comment section? Thanks for watching.